Okay, we're going to do question 5. Question 5 on page 122. This is, again, chapter 6. So we have a sled and a rider. Let's make this ground level. And we have a hill, comes down, then goes back up again, and then comes down to ground level. So this here is height 0. Ground level is height 0. Initially, the sled and rider, I'm just going to make a box. Initially, the sled and rider is 40 meters above ground level. Then over here, the second hump is 30 meters high. And then goes down to ground level. So a sled and rider with a total mass of 40 kilograms. So this sled and rider are going to be indistinguishable. They're together. We're not going to separate them. They're perched at the top of a hill. What does that mean? They're perched. It means momentarily it's motionless and it's about to begin to fall down. So the initial speed is then 0. That's what that means. V initial is 0, but it doesn't stay that way. It moves right away. Gravity's pulling it down. In this case, we do have to worry about friction. In this case, we do have to worry about friction, but for only part of the problem. The author says, suppose that we also know that approximately 2,000 joules of work is done against friction as the sled travels between these 2 points. So I want to make sure I know the points. So between here and here, the snow is not so icy and there is some friction. There is some friction. As the sled and rider move from the top of the first hump to the second hump, we lose 2,000 joules. So question A says, will the sled make it to the top of the second hump if no kinetic energy is given to the sled at the start of the motion? Which just means that this begins sliding all by itself. Nobody pushes it. So for part A, this is a conservation of energy problem. We have a certain amount of energy here. When the object is here, if it gets there, it will have the same amount of energy unless work is done. Well, in this case, work is done. So we have to take that into consideration. So we have the energy initial must equal the energy final. So we have potential energy. In this case, it's just going to be due to gravity, plus kinetic energy must equal the potential energy plus kinetic energy. So this is the total energy here equaling the total energy there. Except that in this case we have work done. The work is robbing some energy. It's robbing 2,000 joules. So we have to write down minus the work done. So the work done is actually positive 2,000 joules, but it's working against the system. Working against the system. So what's the initial potential energy? The initial potential energy has to do with the height, so we get mgh. What's the initial kinetic energy? Well, the initial kinetic energy is 0 because the initial speed is 0. And then minus the work done, 2,000, equals the energy here, assuming it gets there. Let's assume it gets there. So the potential energy, again, would be mgh. Well, we got 2 mgh's. The mass doesn't change, gravity doesn't change, but the height changes. So we're going to call this the initial height and the final height, plus the kinetic energy there, plus the kinetic energy there. So we're going to plug in mass is 40 kilograms times gravity, call it 10. The height is 40 as well, plus 0 minus 1,000. I'm sorry, all right, that's 2,000. Minus 2,000. The work done is 2,000. Is equal to mgh here. Again, m is 40. That's given in the problem. G we know is 10. And the height there is 30. Plus kinetic energy. The thing about kinetic energy here is we don't even know if it makes it there. Second, if it does make it there, we don't know what the speed is. So if the object does make it up to that hill, the kinetic energy will either be 0 or it will be a positive number. If the mass does not, if the sled does not make it up to the hill, then this will be negative. So we're hoping that kinetic energy is equal to 0 or some positive number. Well, maybe hope is not the right word. The idea is, I guess we want them to get up to the top, right? So they can slide all the way down. So I'll say hope. So if the kinetic energy is equal to 0, it would just come up here and stop, be perched there. If the kinetic energy is greater than 0, it will make it to the top, won't stop because the speed will be some positive number and will continue down. If kinetic energy winds up being negative, that means it never made it up there. Let's do the math. 40 times 10 times 40, well, that's going to be 16, and then we have 3 zeros. 16,000 minus 2,000 is equal to 4 times 3 is 12, and then we got 3 zeros. Plus kinetic energy. Well, is kinetic energy 0 or positive? Let's find out. This here goes to 14,000. That's equal to 12,000 plus the kinetic energy. That implies that the kinetic energy, when the sled and rider make it to this point, is equal to 2,000 joules. So because the kinetic energy is positive, it means it has speed, so it's going to wind up going up to the hill and then over. So the question was stated, will the sled and rider make it up there? And this is saying yes. The sled and rider will make it to the top of the second peak. B is, well, an interesting question. Since it does make it there, what is the speed there? That winds up being fairly easy because we know what the kinetic energy there is. We know what the kinetic energy of the mass and sled is when it reaches there. That's equal to 1/2 mv squared. So kinetic energy is 2,000. We just calculated that from the last part A. So that's equal to 1/2 mv squared. M is equal to 40 times v squared. V's are unknown. One equation, one unknown. We eat those for breakfast. We eat them for breakfast. We eat them for lunch. We eat them for snacks. So V winds up being 10 meters per second. That's the answer to B. Now, well, that's it. There is no part C. There was just parts A and B. So this question is done.